Thanks for joining me, guys. Going to start up very soon. Just getting all my streams organised on this slightly lazy Monday afternoon. G'day everybody, thank you so much for joining me live here on a Monday afternoon, 25th of April 2022 for COMP2300/6300, week 8, our first lecture on interrupts and asynchronism, although the asynchronism stuff we won't get to until Thursday. But the interrupt stuff is what we're going to do today. This, my friends, is when this course is starting to get interesting. You folks have learned a lot in the last 7 weeks of content plus 2 weeks of mid-semester break. You have done 7 quite long labs full of detailed information about assembly programming. You have created LED light shows that are just amazing. I'm still amazed about how amazing and cool and interesting and engaging everyone's LED light shows were, with just directly controlling the LEDs with those tiny little assembly instructions. You have completed a mid-semester exam. Congratulations for completing that part of the assessment. And you are now ready to take off and start doing some of the really interesting and tricky things that you can now understand with assembly. Now you understand how your CPU is working in this basic level. You can start to look at how higher level constructs might work. And what I'm talking about today primarily, even though it's not on this slide, is the idea of inputs to your CPU from the outside world. How do we get inputs into your CPU? So far, we've really only dealt with outputs. Outputs by meaning the LEDs, outputs meaning the speaker. And the cool thing about outputs, or the straightforward thing, is that you as the programmer get to be completely in charge of it. You decide when the LED should turn on and off. You decide when the speaker should play a certain sample. You decide what happens, and the microbit does it. And you've gotten to be very good at deciding when things should happen on your microbit. But now when we're dealing with inputs, you don't get to decide when things happen anymore. Why is that? You might have a program running on your microbit, and I'm a user, and I come along with my finger, and I press the button right then. Just press that little button. And what does that mean? That means you don't know where your program is going to be when that button is pressed. So how are you going to find out if it's been pressed or not? That's what we're going to find out today. I'm just going to connect with folks in the chat. Ooh, here we are. Team, I'm just adding the team. Please give me a shout out in the chat to let me know you're there. Give me a react in the chat so I know you're here. I know we have about 20 or 30 people watching on YouTube. We probably have a bunch of people on Twitch, I hope. Although something that was going a little bit wrong with my streaming setup. I used an event in Restream instead of my normal old way of doing things, which meant that I can't see my my stats, which is quite odd because normally I would like to know my stats. Where's my channel? I want to watch other people's things on Twitch. I'm getting, here come the notifications. Thanks folks for joining. Oh, there's only one person watching on Twitch. Sorry Twitch folks. It must be all the best gaming Twitchers are on Monday afternoon on Anzac Day, a very solemn day here in the Australian public holiday calendar, where we remember our armed forces who have participated in wars and had horrible experiences. So everyone must be gaming. That's okay. I'm glad to have so many folks on YouTube, and I'm glad to have about 15 or 20 folks listening in on the chat. Someone says sound is a bit small. I'm just going to turn it up. Turn it up. Should I just adjust my OBS? You're going to have the many Charleses in OBS in a minute. Uh-oh, Charles is all the way down. The sound, look, the sound seems okay. Oh, maybe I need to press this button. I might have pressed that button accidentally. 1, 2, 3, 4, 5. It still seems like it's low. Why is it so low? 1, 2, 3, 4. It's high there. Now I've had this before. Audio. Sound. We did this before. It took me ages to work it out. I'm going to do it today. Ah, there's the problem. There's your issue. Should have the sound. What? Wrong one. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That should be a lot better. One, 2, 3, 4, 5. 1, 2, 3. Is it the right microphone? You know you're a real streamer when you're sitting here getting your audio properties right. That's not the right button. Properties, yeah, it's the right one. Audio has decreased in quality, says Josh. Very sorry about that. Is it increased in quality now? Yep, good. Okay, thank you so much, folks, for debugging that. I don't know. I used Zoom on my computer. Zoom messes with my audio. Far out. Gotta get rid of Zoom. Streaming all the way. Okay, bye-bye that. Back to the lecture. Ooh, now things get interesting. Interrupts. This is the story of this week. We're going to talk about what is an interrupt, when an interrupt happens, and why we might be interested in interrupts. Then we're going to talk about what happens during an interrupt, which is quite interesting actually. Learn about how it precisely works on your microbit. Our theme of this course is having a concept and looking about precisely how the CPU deals with it. Then we'll learn about how this works on your microbit. We'll get to do a demo today. And then later in the week, we'll look at how this is related to parallel computing. How can you run 2 programs at once? And what does interrupts have to do with that? But first, let's just have a bit of an admin break. Folks, you have completed 45% of the assessment for COMP2300/6300. So I think you deserve a pat on the back for that. You've done amazingly well so far. I've seen unbelievable feats of assembly programming and design document writing and explanation at this point. The mid-sem was on Friday. That means the ETA for results will be the end of next week, end of week 9. Week 8 though, assignment 2 is coming out, and I've got a new challenge for you, which I'm going to show you in a minute. Very exciting stuff. Finally, the other aspect of the assignment is in week 9, which is next week, you will be having your assignment pre-submission week. So you'll find out about the assignment in a minute, and immediately from today, I want you to start thinking about your pre-submission, your design proposal for next week's lab. Now, one big thing. I know we've had a lot of assessments happening at ANU. Everyone has been very busy. There have been assignments and deadlines and crazy stuff, but we've seen the lab attendance drop off a little bit. I need to tell you this now. Do not forget to go to your labs. The most important thing you can do to this course is go to every single lab and complete them in the time allotted. Make use of the time to talk to your tutors about your work. The labs directly support your success in the assignments, and the labs and assignments put together directly support your success in the exams. So it's all part of one big cycle. You can't drop out of the labs and expect things to work. All right, folks, let's see what we're going to make for your assignment 2. Here it comes. You're going to make a digital pet. How cool is that going to be? I can hear the excitement already. In case you don't know, a digital pet is one of these little plastic doodads. I've got 2 here, little plastic doodads. These were a thing in the 90s when I was at primary school. They're a little toy. They have a little program in them and a little LCD screen. They're only black and white and a very simple screen and a very simple computer in them because they're quite old technology and they sort of go beep boop sometimes. But the idea of a digital pet is that you get to have a little character living in this toy in your pocket. You get to look after it, you get to play with it, give it some food, give it medicine when it's sick, and see it live and grow and have an exciting and fun experience. So it's I can see the excited reacts in the chat. I'm so pleased to have that reaction. This is what you've been waiting for, I think, because what you need to do to make a digital pet. It puts together everything you've been learning so far. You need to have an engaging and interesting display on the screen. So you're going to use the screen in a more directed way than perhaps you did in assignment 1. You need to have a character in memory, record its stats and things about it in some kind of data structure. So you'll need to use your knowledge of memory and data structures. You'll need to be able to build a complicated program that's got multiple things happening at once. So you'll be really pushing your understanding of control flow and the flow of execution in assembly. And the thing which we haven't done yet, which you're going to learn about today, is you're going to need to use these bad boys, the buttons on the front of your microbit. You're going to use those to control your digital pet and give the user some way to interact with it or play with it or look after it in some way. So, where's my remote control? I'm going to go back to the slides for a minute. I've got a boring flat slide about the digital pet assignment here, but I'm going to show you the assignment 2 page, which I've just finished up today. Assignment 2, digital pet. Create a lovable digital pet on your microbit. This is going to be pretty cool. So just a few things. Again, it's a pretty clear assignment. You just have to do a thing. I'm setting you a fun, interesting challenge, and I want everyone to go out and have a million different ideas and take it in a million different directions, or at least 400 different directions, which is pretty much what happened with assignment 1. I was really pleased at the diversity and variety of approaches to that assignment. So do the same thing here. But here's what you're going to need to do for your digital pets. You're going to need to write in assembly code, first of all. That's a basic for this course. You'll need to use the LED display. you'll need to use at least one data structure to record your digital pet's state or abilities or play experience or something. You must use interrupts to detect interactions with the microbit buttons. It must work when you're powered over USB, so same deal as for assignment 1, you can't be in the debugger stepping through to make things work. It must be engaging and require interaction. Yeah, that's the tricky one. So your digital pet here, it's written up here, your digital pet should provide companionship, that is, it's engaging to look at, but also responsibility, so it requires interaction. Yeah, I'll let you continue reading the assignment spec at your convenience, but honestly, it's quite clear. You just have to make a digital pet using the buttons and just go do it. We've got 2 weeks of labs that are going to scaffold this for you. By the time you finish week 9 labs, you will have experience writing an interactive program using the buttons, using timers, using the LED screen, putting it all together. And then you'll get to go out and finish off this assignment, which will be due at the end of week 11, I'm going to say. I believe that's correct. In week 11, I think that's a Friday. So you've got more time for this assignment than assignment 1, and you've got the scaffolding building up in the labs to train you how to do it. So once you've done lab 9 and completed all the exercises from lab 8 and lab 9, you'll be in a very good position to get started, and you can be confident that you'll be able to create something like a digital pet in assembly programming. A few factoids about digital pets. These things came out in the 90s, as I said. There's something that was happening in my childhood when I was at primary school. They were so popular, kids would hang them off their keychain. I'll go back to the video for a minute. Kids would hang them off their keychain and they would go off, beep, 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 in class. And they got so popular that they had to be banned from school, which was bad for the people selling them because they relied on them being a craze and kids wanting to have tons of them. I never had this is the good kind, the official Bandai Tamagotchi. This doesn't belong to me, this belongs to my wife. This is her digital pet. And I used to have one, but it's lost. I never had an official one, I had a knockoff one, the cheapo ones, and I bought another knockoff one. This is a cheapo one. This one is so bad, I got it off AliExpress. It's so bad that it actually crashes after about 5 minutes and you can't play with it anymore. But I'll show you what happens when it starts. You press reset. It has a reset button on the front because you have to reset it because it keeps crashing. Then you sort of choose what digital pet you want. And then you press decide, you get a pet, or you decide the time. That's boring, you decide its name. You probably can't start this, see it really well, but there's a digital pet doing some stuff. And then it kind of hangs around the screen and you can play with it. And on the good digital pets, on the Tamagotchis that work, they'll be like, you play with it, gain some experiences, you can do more interesting things after a while. Over days of playing with it, it grows, and you don't have to do this in your digital pet because these ones are designed to last, be fun for a couple of months. Yours doesn't have to be fun for that long. But over days it grows up, you see it grow and change and do things with it, then eventually it grows old and then eventually it dies. And the tragedy for children of seeing their little digital pet die was quite palpable. Anyway, that's enough about digital pets. But I'm sure it's going to be a fun assignment. I'm really looking forward to seeing all of the exciting things you do with this concept. Yeah, this one died. I think it's got a skull. Or maybe that's its waste product, digital pet waste. Okay, back to the content. Only 25 minutes to get to the content. What is an interrupt? Now think about this. You've got a phone. Do you check your messages only at certain times of day? Or is there some other way that you get input from other people in the universe? And of course you don't get input for just at certain times of day. Generally, everyone waits for their phone to ring and then they answer it and say hello. And if someone calls, they always answer. I guess sometimes people have a certain kind of life hack where they just check messages at certain times, but usually we're responsive to interruptions or some kind of alarm going off or a notification or a signal that we should sit up and take notice and do something. And this difference between a signaling approach and a controlled internal control approach is what we're going to talk about now for a minute. With another analogy. No, well, haven't got quite to the analogy yet, but on the microbit, this communication thing is about external inputs, sensors, GPIOs taking input as well as output, and whoops, it's an equivalent of putting your phone on silent. Indeed, yeah, there could be with interrupts. We'll talk about that soon. So far, you've only been doing this option, CPU running its own sequence of instructions. And we're going to talk about today this one. How's it going to handle communications with the world? But let's go for an analogy. Imagine that your microbit is a starship. Okay, a starship has some kind of outputs. I guess in this starship, it's the phasers that go and destroy other starships. We're going to call this like a generic star journeying device that could be called, you know, the expedition, going on a star expedition through space to learn about new things. So it's got some kind of outputs, the lasers or phasers or proton torpedoes or other such things. It could have inputs, so it's got long-range sensors that will put them in green because inputs are usually good. And of course, it's really a vessel of exploration. It's taking inputs into sensors, and it probably also has some kind of internal sensors that are taking information. Maybe its engines back here have to send information somewhere. So we're getting information from other stars, long-range sensors, short-range sensors, proximity sensors. Oh, we've probably got the tractor beam as well. That's an output of a sort, an actuator. So we've got inputs and outputs on our starship. Now, every starship has a captain, and folks, this is assumed knowledge, so don't expect me to be pulling any punches on the exam for that one. Every starship has a captain, and this is the captain of this starship, Captain Jean-Luc Picard. And of course, there's the crew who answer questions. And if we're thinking about a CPU, Jean-Luc Picard's going to be the CPU, and everyone else is going to be the peripherals. You know, so maybe Commander Riker is GPIO, and Counselor Troy is the random number generator, and I don't know where I'm going with this really. I don't know. Geordie LaForge, where's he? Oh, I don't know. Anyway, Data is going to be a timer, and Wesley's going to be the UART, the serial connection. We'll talk about UART in a few weeks. Anyway, so they're all the peripherals, and Jean-Luc Picard's the CPU. How does Jean-Luc Picard, as the CPU, get information out from the world? Well, the first thing he does is just ask his peripherals, give me some information about the world. Give me a damage report of my ship. And then all the peripherals come in and they take their turn and provide information to him in that moment. What are the other options? Well, if something really bad happens or something really important happens, well, Commander Riker is not just going to stand there. He's GPIO, remember? He's not just going to stand there and wait to be asked. He's going to stand up and make Captain Picard take notice. So he's going to say, Captain, look out. This, folks, is an interrupt, because in that moment, Jean-Luc Picard might have been drinking his tea Earl Grey hot, but he is going to have to stop doing that and do something else because the GPIO has told him that there's something important going on. So this is an interrupt occurring. There's a flow of execution in the CPU. Something important happens on one of the peripherals, and it needs to tell the CPU to come and handle this right now. The CPU has to stop what it's doing and basically run a different program for a little while in order to handle the interrupt. Okay, so this analogy was to say that there's basically two styles of interacting with these kind of external pieces of data. Polling one style and interrupts is the other style. They're both useful. They're just different. And one of them is particularly interesting because of how it uses specific hardware within the CPU to do what it does. So the idea with polling, it's the status report idea. Status report. So maybe we have some big function, a main function in our program, which is going to loop. So it does some stuff and then goes to the end and happens again. So we're going to check each external device at a certain time. We'll go check keyboard, check mouse, check camera. And we might do some actual work for a while. We've done some checking for a bit. Fly the spaceship. Whoops, poor handwriting. Spaceship. There. So this is like what's going on Riker, what's going on Geordi, what's going on Data. Fly the spaceship. Check USB 1, check temperature, do some other stuff. This is actually the actual work we're doing. Fly spaceship. Check USB 2, check network, etc. So this works. Often this works fine. There are definitely going to be some limitations. It could be that something on the keyboard happens very quickly and that only happens on the keyboard at this time. So if it happens when we're down here, we're not going to know about it because we only check the keyboard up in this part of the program. So if the keyboard only occurs occasionally, but it's for a very short time period, we might miss it. So that's a problem with the polling idea. You might miss something. Other things like check temperature, maybe not so bad. Like temperature is always going to be there. There's probably not going to be an alert because temperature changes slowly, unless we're in some reason that there would be. But in general, things like temperature change slowly. They are a constant thing happening. They're not something which is transient or happening for a short time and very important to react to. So we could check that with a polling approach. Here's the second idea, the interrupts idea. We're going to change our processor architecture. It has to be built into the hardware to allow an external part to interrupt our fetch, decode, execute cycle. So the sequence of code is interrupted and the CPU automatically branches to an interrupt handler. And this is going to be ideal for the keyboard situation because we could have our main function. It's much simpler now. We only have to do our actual work. So we're spending all of our time flying the spaceship, doing the actual work we need. And then whenever someone presses a button on the keyboard, the CPU is going to stop what it's doing here and branch into the keyboard interrupt handler, do this, and then find its way back. So the keyboard interrupt handler down here is going to be some kind of function that we can branch to automatically when someone presses a button on the keyboard. Well, so far so good. And it doesn't actually seem that complicated. And in some way, it isn't. It becomes complicated for two reasons. One is that we have to understand a few details about how the hardware makes this work so that it does work. And secondly, we have to accept that we have no control over when the keyboard interrupt handler will run. And so our program has to be prepared to handle that information at any time or have some way of turning off, say, I'm not listening to the keyboard right now, I need to do something else. It's a very important bit of spaceship flying I'm doing right now. And even if you press a button on the keyboard, I don't care. I'll look at it later. And that's possible too. So we need to know how to do these things. How does it work in practice? Let's just think from the CPU perspective. How is this interrupt going to change the flow of execution on our CPU? Well, if you recall our basic CPU model of having our registers, our ALU to do calculations, some flags coming out of the ALU, data, memory, something bringing in the lines of code, and then something over here to work out what to do with each bit of code as it's coming in from memory, a decoder and a sequencer. And the interrupt is going to come in here and change something about the code input and point our PC somewhere else rather than where we would point it to originally. So it's not just an input actually, it's going to take some output as well because it has to take some stuff about the current state and keep track of it while the interrupt is occurring. Okay, polling versus interrupts. Sometimes it's interesting to frame these things as kind of a trade-off, two different approaches with different pros and cons. I guess the pros of the polling approach is that it's fairly simple to implement. You don't need to know how interrupts work. It's going to be, if you have a small number of devices that you're dealing with, it's probably faster, and it's going to be easy to calculate latency if you really need to know how often you're checking a sensor. Polling is a good idea. But downside, devices need to wait their turn, and if a event or a sensed bit of data is short, you might miss it. And also, if you're having to deal with a lot of devices, the main function is going to be very long. So, a few cool things about interrupts. You get things that you can't have with polling. You can have preemptive scheduling. Don't expect you to know what that means yet, but it's to do with the way operating systems work. You're going to have timer-driven actions. That means you can do something better than the delay tactics or the delay functions you've been using so far in your assignments. You can look at hardware interactions that are transient, like clicking a keyboard, etc. There's lots of advantages to this, and we're going to learn a few about them today, and you'll learn a lot about it in your lab this week. Problem with interrupts, a little bit more work to set up, and you need to have a CPU that supports it. Thankfully, pretty much every CPU supports interrupts. There's not a question. Normal CPUs do support interrupts. There are some esoteric ones that don't, but in general they do. Why is this important? Big picture stuff. So far, everything you've done in your microbit has been like clockwork. Fetch, decode, execute, etc. In assignment 1, you knew the order of everything. So you could have one big program, and some people did have a huge program that just did every single change and adjustment to those LEDs. Now, you've got a situation where an interrupt could happen at any time. So you have to be prepared for the unexpected. Expecting the unexpected is the name of the game from now on. Okay, an interrupt could happen at any time. A question for you folks. What does this mean for you as a programmer that an interrupt could happen at any time? As an assembly programmer, and I want you to jump in the chat and give me a suggestion. What are you going to have to worry about if an interrupt could happen at any time? You tell me. Whoops. No, don't go forward. I'll sit here and wait. I'll play my game for a minute. That was the good thing about these things. You could use them to procrastinate in class. You need to. Josh just said you need to have a check for interrupts during the program. Ooh. So is what you're saying that in order for interrupts to work, I should be polling my interrupts? I don't think that quite makes sense. Someone has said you don't want the interrupt to depend on partially executed stuff. Good point. Yep, could. Oh, someone's got a really good suggestion here. It could mess with your registers. Could mess with your registers indeed. So elaborate. Someone says it could mess with your registers. So how could it mess with my registers? What registers would I be worried about being messed up? My two things here were don't want dependence on, whoops, partially executed stuff. Mess with registers. Someone says I should worry about things crashing. Well, I guess I could worry about things crashing, but that's something I would always have to worry about, whether there's an interrupt or not. Ooh, someone's got a really good suggestion here. And someone's also got the answer. Someone's saying, I think I heard that this is the way it works, which is, I'm probably going to tell you about in a minute, but let's just go through this logic here, mess with registers. We've got this handler function, which is going to be called handler. And normally your functions would save your callee save registers, right? R4 to R12, I guess that includes all of them, and LR. You're going to have to make sure you go back to the right place after the interrupt. Exactly. Go back, find way home. Yeah, so the handler normally would push R4 to R12. And normally our calling code would deal with R0 to R3. So there's going to have to be some way that the interrupt looks after these registers and make sure they don't get lost. We're also going to have to find our way home, make sure that we don't get... Oh, something happened in my... What's that? It's unhappy? I don't know. Give it some food. This also would happen. People would be in class having to give their guy some food. What? No, it won't have food. Maybe it's sick. Oh, I don't know. How do you heal it? Doctor's kit? No, it's completely wrong. Oh well. Consistency. Okay, yes, so a few good ideas here. One is knowing where we are in our program. Folks, when we have interrupts, you're going to have much less surety about where you are in your program at any particular point. So you don't have to worry too much about this actually, because the idea of an interrupt is that your program would go right back the way it started. It was going after the interrupt has concluded. Ideally, your program wouldn't have any idea about how an interrupt should or where an interrupt has occurred. There might be interrupts that occur, your program doesn't even know about it, and it goes back the way it was going. Oh, someone suggested that I could just make the handler push R0 to R3. Mess with registers. Find way home. So we're going to have to know somewhere about deal with our link register. So I have to look after our link register somehow, and I'll explain how that works in a minute as well. You could just have the handler push R0 to R3, but it's actually not what we do. There's another, in fact, better way to do this, so that our handler can just be a regular function, just following the regular calling convention. Don't want dependence on partially executed stuff. I put this at the top. It's probably the most complicated and detailed thing to discuss, and I probably have a whole lecture on this concept on Thursday. So what I mean by complicated is, if a register can happen at any time, you could be in the middle of something else. And is there any situation in which, if you're in the middle of something else and a register occurs, your program goes wrong? And sometimes it's hard to imagine how that could happen, but it can happen actually a lot. And it typically happens when you're wanting to store something into memory. So if you're storing something into memory, and for instance your interrupt handler also wants to store something into that memory, you might end up in a situation where you don't know which thing has actually succeeded in store. What if they're trying to store into the same bit of memory? You don't know which one happens first. And you might have no way of knowing which one has been successful and which one has overwritten the other. So there is a way on your microbit to get it to make sure you have some idea about which thing has written to memory first. I'll tell you about that on Thursday. We're going to move on in a second but thank you so much for the engagement, these great ideas. I'll answer one question about the assignment. Someone's just said, what if you make a program that takes like 3 days to run? Don't make a program that takes 3 days to run. Make a program that takes a few minutes to have fun with. I think it's either in the FAQ right now, or I'll put it in there. I just have to remember what I put in the FAQ. Yeah, your pet doesn't even have to have a whole life. It might just have a few interactions. Realistically, many people are going to have quite simple pets. A few people will have very complicated ones. So I'm not making prejudgments about whether your pets should die or not. They don't have to. They don't have to have a life cycle. They just have to be interactive and engaging. All right. Whoops. Interrupts. Expecting the unexpected. Our computers now need to respond. to external events as well as errors. Oops, sorry. Too much animated talking during this fun Monday afternoon lecture. Interrupts are going to happen, and they're going to happen all the time, or they do happen all the time in regular computers, e.g. your keyboard. Every time you hit a key, it's really an interrupt occurring. This is going to really break our assumptions about fetch, decode, execute cycle. We need a process to follow that saves our contexts and allows us to get back to it later. What is context? It's all of the stuff that you care about in your current execution. Your register contents, PC, where you are up to in your stack, all of this stuff is your context of execution. So if you break that context, if you go to an interrupt and come back, if it's broken when you come back, your program is going to crash, or it's not going to work the way you want it to. Context, important word. How does it work? Here we go. How are we going to store the interrupt code, and how does the microbit know how to get there? So here's a little demo in image form. Your pre-interrupts. This is your world so far, where everything is fine. You have some code, and you know your PC, your program counter is pointing to a particular line of code, and it's pointing to the line of code it's just about to execute. And you've got a stack. You might have 2 frames in your stack. You've got your first function f1 and a function f2, and there's your previous stack pointer, your current stack pointer is here, and you know your frame is starting about here, and you've stored a bunch of stuff on the stack while you're running your function, stored your parameters, stored your context, stored your return address. Doesn't matter what order these things happen as long as they're there, and you've stored your local variables. So your program is ticking away, all very happy. And then an interrupt occurs. So this is how this works. Your microbit is going to make the PC go to the start of a handler, which is a function. That's a function in some other place. I've got them separated here, but really, it's just somewhere in your code. You've got a handler. It's separated here, and your PC has moved from down here up to there. So the first thing that happens when the interrupt occurs is that your previous PC and your flags are saved on the stack. So this is your context. PC and flags are saved on the stack. Now the PC is inside an interrupt handler, a function which has been set up previously to look after this interrupt for you. So you've already set up that function to look after the interrupt, and you know that your link register has something in it. It doesn't have exactly what you had before. It doesn't have actually where you're going back to. Excuse me, sorry, I'm confusing myself here. If your link register, normally when you run a function, your link register points to the previous value of PC, right? But it can't do that in this case because you need to have this special interrupt hardware storage of context on the stack automatically. This needs to happen automatically for you. So you get a special value in LR, which doesn't point to anywhere in memory. It's the value which is like, I'm in an interrupt right now, and when we're done with this function, we need to unpick the interrupt storage on the stack. So interrupts are automatically using the stack. Here's what you might do in your handler. Push some registers, declare local variables, etc., your normal stuff, do your input-output stuff, run some time-critical code. There's all kinds of reasons you might have an interrupt run. It could be because someone's pressed a button, or it could be because you've set a kind of alarm clock in your code. Do something in 1 second, and you need your code to jump. When that 1 second is up, jump back to the interrupt, do something, and then continue. If there was something in LR before the interrupt, would it get overwritten? Someone is saying that? No. I think I'm actually missing some steps here. There's more stuff that gets put on, including LR. I've forgotten the order of things, but I'm going to say LR, R0 to R3. Actually, LR is your you push LR anyway. I'll have to think about the question in a minute, or we'll just investigate it because I've forgotten. It was 2 years since I gave this lecture, so I've forgotten exactly what happens. And I'll have to remember it using a microbit in a second. This is what you do. The interrupt handler has done this. You run your regular handler stuff. Then you pop off your registers. Your PC ends up at the bottom of the handler. Someone asked that really good question and just made me realize that my slides are broken, which is annoying. I'll fix them all up, delete it, and re-give this lecture. No, I'll just make a small edit. And then we return from our interrupt, BXLR, and the special LR is going to get the CPU to put everything back the way it was. So actually, what I'm missing here is that there was some other context that the interrupt automatically puts on the stack for you. So there's a little tiny bit of this stack missing. We'll worry about that later. We'll learn about what it is when we do some experiments. So from the handler's perspective, it's just a normal function. It has to push callee saved registers. It has to look after its own LR that it sees when it starts. And then at the end of that function, it simply runs BXLR, and then the special LR tells the CPU that it's returning from a register and it needs to put everything back the way it was. Put all the context back and return everything back as if nothing had happened. How magical. And SP returns to its beginning state. All right. The interrupt timeline. Save PC and flags on the stack and other context. Now the PC is inside the interrupt handler. The link register has been set up with a special value, and then we do our normal function stuff. And then at the end of that, we return. Someone's asked a question, what if we want to change registers / old parameters and not restore afterwards? Two really good questions. Another one's come in. So we don't need to do the AA-PCS rules when using interrupts. I'll answer them in reverse order. Here's the rest of the context which has been put on the stack. Like R0, R1, R2, R3, some other stuff. I've forgotten what it all is, but a bunch of stuff gets put on the stack. And the handler. Our interrupt has just fired. Now, our handler obeys AA-PCS. Okay, it needs to save anything in the callee save registers, R4 to R12. It needs to save its own value of LR, because the LR it's got is the special value. It needs to go back to the previous state. It could be calling other functions that need to use LR as well, so they need to get back to it. Normally they would, right? Your interrupt handler would call other functions in order to get its work done. Very common. So this handler is obeying the PCS as a callee. This code over here has no idea that a function has been called. So it's impossible for it to do the caller saved stuff. Normally before you call a function, right, you type like push R0 to R3. Right? If I go into my code, here I am the main thing. I want to call a function, BL function 1, and before I do that, I want to push R0 to R3. And then at the end, I pop them back if I need to save their value. So these are the caller saved registers. But my problem is I don't know when the interrupt handler is going to happen. So if my function was an interrupt handler, this is completely wrong. There we go. Someone's found the text from the manual for me. So normally when you call a function, you have to save the caller saved registers. But my point here is that interrupt handlers are functions, but you don't know when they're going to run. So it's impossible for your code to do the caller saved registers. That means we don't need to do them. We don't do this. We don't run the function. Interrupt function runs itself. We don't know when. We can't do this. Can't do this. We don't know when function will run. And we can't do restore it either because we don't know when the function happened. Ideally, from your code's point of view, nothing has changed when the interrupt occurs. And someone in the chat has thankfully just gone through the manual and said that the things that are saved to the stack are exactly 8 32-bit words, which is going to be the XPSR, that's flags, the whatever was in LR, the return address, which is PC, R12, and R0 to R3. Can an interrupt handler be interrupted? Are you looking forward through my slides? I think I've got a slide in a minute dealing with that. Also, I'll hold on that question. Someone's just said, that's for an exception happening, not an interrupt. Folks, prepare for your mind to be blown. Exceptions and interrupts are the same thing. And interrupt, same procedure. There was another really good question. The question was something like, so if my interrupt handler starts, that means I'm not allowed to change the values in R0 to R3? No, you can change them. You just go backwards through the stack. If you've got these things in the stack, while you're in the interrupt handler, your interrupt handler code can be looking at things in the stack and changing them if it wants to. The stack is read-write. Your program has access to it. It's allowed to change them. So, in fact, it's a very good idea to do this. It will be a good idea for doing what we call context switching, where you want an interrupt to allow you to change to another program, which is what we're going to talk about on Thursday. So I'll leave that question for now. I'm glad I could teach a few people a few things today. I start to worry when students get way ahead of me, like you folks seem to be in the chat. I don't have anything to teach you. You know everything. Okay. That was really good. Thank you for finding that stuff in the manual. I just can't believe that I forgot to put that in these slides. It was quite a while ago that I made these images. And I think what had happened was I was looking at someone else's slides, which were sort of for a generic processor, not exactly for a Cortex-M4. But most of my other slides, as you know, I really like to talk about specifically what happens on your microbit, because I think that's most useful for us to learn exactly how it works on the microbit, and then we can generalize to other processors as you read the manuals for those processors, because it could be different. Things to consider. Oh, yeah, I got through that slide. Interrupt handler code can also be interrupted. Huh. Interesting. How would that work? Well, we have to work out which interrupt is more important. Someone in the chat said one could be more advanced. In fact, we have this concept called priorities for interrupts. So an interrupt with a lower number for priority is allowed to go first. In fact, it might look something like this. We could have this diagram where your regular program, this is main here, regular program's going along, some interrupt is triggered, here this interrupt handler starts going, then there's another interrupt triggered, another interrupt happens, and then the second interrupt, that might have been priority 4, and this one was priority 5. So this one is interrupting the first one. Handler 2 exits, BXLR returns. It doesn't return back to our main function. It returns back to the first interrupt handler. And then back to main. So here we are. Interrupt handlers are functions. Interrupt handlers are functions. So you get to write these functions, but you don't get to choose when they run. So they're a function in your code, just like every function you've written before. It might be called handler with a label, have a bunch of stuff, and then have BXLR at the end. But you're never going to write BL handler. You might, but it's unlikely. You're most likely to let the interrupt handle run itself when it needs to. And we'll learn how to do that soon. Interrupts in practice. Where am I up to in my slides? I'm actually going to take a short break here and just get a glass of water. So I'll put you on break mode. You can go get a glass of water as well. Adnan's going to have time to get back from his interruption. And we're going to do an interrupt right here in this lecture, which is going to be pretty fun. So I'll catch you folks in a few minutes. I'm back. All right, just small. Thanks, folks, for waiting for me to come back. Make sure everything's good with my stream. Few chats while I was away. What are people chatting about? Oddly calming. Smooth. What was my Latin music was for the middle bit? I think I've got some YouTube music which is like a nice bossa nova groove. Thank you for enjoying that. I rarely take it. I rarely use the break function in my OBS. I'm not that advanced a streamer. I need to have my little macro pad for all my breaks, but I don't have one. I don't think they work very well with Linux. I had a macro pad I was trying to get to work originally with my lecture rig, but it wasn't that happy. Just going back through questions. Do we need to set a condition for the occurrence of an interrupt? You absolutely do. We're going to learn how to do that in a minute. Ooh, okay, everyone's calmed down. Okay, let's pop this, restore the context in our brain. I've got a cup of tea. Sorry, I do tend to yell in lectures, even though I've got a nice microphone and I'm just in my office, but I get excited about it. So we're making digital pets. It's fun stuff. We're doing interrupts. What could be more exciting, folks? Now, you've probably experienced an interrupt already, or an exception, and I will suggest why. You might have something like this. Suppose you've got some code with a couple of nops. Just does nothing. You know, totally valid program, okay? What's wrong with this program? Well, if we run it, we're going to knock ourselves off a cliff because we don't have any way to get back to the start of main. And once we finish that, we end up in the very next bit of code in our startup script, which isn't actually code, and it's not going to know what to do. We're in our reset handler, so it's we're really stuck. The default handler. Yeah, you guys know about the default handler. This wasn't a good example. I need more nops or something to get myself into some weird part of memory. Or I'll have another function down here. Nothing. Nop. B nothing. Or BL nothing actually. I gotta put these folks. Put my little pets to sleep. I'm trying to get it to do... Now I want my program to crash and I can't get it to do it. What? I can't get into the default handler. Anyway, you know what I mean. You end up in this thing in the startup file called default handler. And the reason you end up there is because this is the interrupt handler, which is the default for any exception that we haven't set up yet, or any interrupt we haven't set up. And we actually have in our startup.s file, which is defining all of the the very small amount of setup we need just to get our microbit going. We provide you with as little setup as possible, so you're really working with a very bare bones system. But we've got all of these interrupts listed here in what we call the vector table, which is a list of locations for where every interrupt is going to be. So the first interrupt is the reset handler, second one's called a non-maskable interrupt handler, hard fault handler, memory management handler, bus fault handler, usage fault handler, That's if you've got something wrong with an instruction or it's not doing the right thing. Then there's a couple of that aren't implemented and some other things, and then all of these ones after this point, are specific to your microbit, not the ARM Cortex-M4. So these things are built into the CPU, and these ones are part of the microbit's peripherals. These are like the Commander Riker, Counselor Troy. And at the moment, all of these interrupts are set up so that they point to the same default handler. Well, they almost all are anyway. If we go down the bottom, you can see that they're all set non-maskable interrupt handler, default handler, set hard fault handler, default handler, set memory management handler, default handler. More useful ones, whoops, where am I? More useful ones are down here. GPIO, you should be recognizing those important letters. We're going to look at these ones in a minute. GPIO-TE IRQ handler is set to the default handler. So the first thing we're going to do when we want to take control of an interrupt is to change the link between our change the link for one of these interrupt pointers to point to our handler instead of the default handler. So you folks know all about the the handlers. I should be trying to write to flash memory. That'll crash it. Yeah, that'll give me a usage fault. So if I go like store R0, mov R1 0, store R0 R1. Good point. This will definitely crash my disco board. Not a disco board, it's a microbit. Bunch of nops. And try to store something. Well, it worked. Well, I don't know what I'm doing. I can't do something which I can't get my thing to crash. It always crashes until today. Delete that nothing. Okay. Someone send me in the chat, send me a program which is guaranteed to crash. The shortest possible crashable program. I'll wait. No, I won't wait. I'm going to talk about it. So, how do we configure an interrupt? We need to enable the interrupt. Then we need to define a handler function. Define a function which is going to handle an interrupt and reset that link in the interrupt vector table. Then we need to configure our hardware to get that interrupt to fire at the right time. Actually, a different order. That's step 2, and that's step 3. This is what we're going to do. So I've got a few things here in the lecture slides, which are in case you're reading this in slides afterwards. A list of the start of the interrupt vectors. The vectors mean they're a sequence of numbers. Each number is a link to a memory location, a vector table, that's what that means. And all of these links to memory locations are defined in startup.s. They're the official vector table for this microcontroller. Different microcontrollers have different vector tables. Still waiting on a 100% crashing program. It has to be a program which crashes on runtime, but it does compile, which is sometimes a bit tricky. How do we take over an interrupt handler? Well, I talked about this GPIO-TE interrupt handler, and all we have to do is rename it. So we create a function with this name, and then we export its names to other files. So .global is saying that the name of this function or the name of this label should be exported to other files within your project that are all getting compiled together. So I can write this in or just copy and paste it into my code. And now it should be overwriting my startup.s GPIO-TE IQ handler. And we know that this one is going to be overwritable because it says here .weak. Very weak. It's easy to overwrite it. It's a weak link, so it's going to be overwritten by our strong link in the other file. Now. I'm going to spoil myself by, I've got a few more slides. I don't want to give away all of the code immediately. I want to work it out together, or test myself, test my understanding by making myself write it from scratch. So we want to use the buttons in our microbit. How are we going to do that? Is that similar to activating the LEDs? In some ways it is, and in some ways it isn't. So we're definitely going to be setting something up in our GPIO peripheral, but we're actually not going to be using the same peripherals we were using before. Before we were talking directly to the GPIO and saying turn on LED, etc. Now we're going to talk to a different peripheral called GPIO-TE. And this is a specific peripheral for managing interrupts related to GPIO pins. It's a specific peripheral designed for managing interrupts on GPIO pins. So it's got two roles. T stands for tasks, which is kind of output things. We're not dealing with that today. And E is events. And the events bit, these you can really read that meaning interrupts. Whenever an event happens, it's possible for the GPIO-TE module to trigger an interrupt. So we're going to be configuring something, but mainly configuring this one and not this one. But the same sort of ideas apply. We need memory addresses for these things. We need to do load, twiddle, store. We need to set up certain values. We need to be very careful. We need to read the manual. Here's a little diagram of how this works. So bear with me for a minute. Your microbit's buttons are connected to two GPIO pins, P0.14, that's button A. If you look closely on the front of your microbit, you'll see that there's two little letters, A and B. So button A is the left one and button B is the right one. Actually, there's a third secret button on your microbit, which is this logo. And the logo doesn't have a switch. It's just a button. It's just really an exposed pin of the GPIO. And when you touch it with your finger, it tends to change the voltage of that pin. So you can use it as a sensor by touching just the electrical contact there, which is pretty cool. So you have three possible buttons to use. We're going to talk just today about the two regular type buttons. So your GPIO ports, you're very comfortable with controlling those so far. And your GPIO ports have this direct input-output connection to your Cortex-M4 processor within your microbit. And you know that you've got all of these different ports and pins. And you know now that button A is connected to port 0 pin 14 and button B is connected to port 0 pin 23. Finally someone sent me a cool handler. Yeah, that will definitely go to the default handler. I know why. Someone sent me a cool crashing program. I'll talk about this first, then we'll go and make the microbit crash. So we can certainly look at the GPIO pins and read their values. You can change them to input direction. You can read the value on those. I think there's an input register for each port, and read the value at a certain time. But that's like polling. We don't want to do polling. We need to do this interrupt thing. And what we have to do for the interrupt procedure is to get our GPIO-TE controller to watch the values on certain pins. It's going to watch the value on pin 14 or pin 23. The GPIO-TE controller has the capacity to watch 8 things at once. So it's got 8, we call them channels. And so we're going to take one of those channels and say, look at pin 14 for button A. Then we're going to have to set up another piece of hardware called the Nested Vectored Interrupt Controller. which actually is the interrupt controller of the CPU. And we have to tell that to accept interrupts from the GPIO-TE controller. So the NVIC has lots of lines, similar to GPIO lines, just a wire inside the CPU, which can be used to trigger an interrupt. And each one of those lines corresponds to one of the memory locations in our vector table. Recalling that there were all these different ones connected. And in some sense, like reset, that's interrupt 0, this is interrupt 1, interrupt 2, interrupt 3, interrupt 4, interrupt 5, etc. So there's different numbers for each one. So the NVIC can handle all these different kind of things, and we need to say, open up your ears and listen to interrupts from the GPIO-TE controller, and send those interrupts to, or act on those interrupts with the processor core. There's another piece of hardware which we're going to look at in labs this week, a timer called sysTick, which is the built-in timer of your Cortex-M4, which can also trigger interrupts, so you're going to deal with that. Pin for the third button, someone's got a question. I think it's somewhere in here. Touch. Oh, you actually have 4 buttons. The ring connectors are also buttons. I've forgotten what the pin is. You'll have to look in the reference. Okay, so now we're going to deal with this. This interrupts, connecting it all up. We need to configure the GPIO-TE module to listen on PO14 and configure the NVIC to make this happen. This is a little bit fussy. The good news for me, and you probably, is that it's much less fussy with the microbit than it was with the boards we used last year. Last year I had to remember 8 steps, which I couldn't do, or last time I taught this course. Now I only have to remember 4 steps, which I can just about do. Let's learn about the GPIO-TE module. I'll go to my reference resources and have a look. Whoop, product specification. This is a microcontroller thing, not a Cortex-M4 thing, so I need to look in the microcontroller manual. Okay, you're not going to be able to likely see the table of contents here, but I'm going to scooch my way down to chapter 6 point something, 6.9, which is just after GPIO. So you should be comfortable. You should have had a look at this chapter on GPIO in order to do the assignment 1 task. And you might have seen these things about sensing and detecting and events and just thought, I'll just leave that for now. But now you need to deal with it. The GPIO-TE, GPIO Task and Events module, provides functionality for accessing GPIO pins using tasks and events. Each GPIO-TE channel can be assigned to 1 pin. A GPIO-TE block enables GPIOs to generate events on pin state change, which can carry out tasks, and one of those tasks is an interrupt. So, have a look at the configuration here. Tasks and events pin configuration. I've got my list of registers, not too many. Having some trouble navigating here. Uh-oh. Registers, I really want the tasks. Oh, events, that's the one I want. Config. So my config register, well, first of all, my base register here is OX40006000. And my config register, I've done it again. The config register lives at offset 510, and it's got a number of different places I have to set within that config register. So it gets a bit fiddly here. We've got to set the mode for our GPIO-TE. We want to put it into event mode, that'll be 1. we've got to set the GPIO pin number associated with it, which is going to be 14. We've got to set the port number, which will be 0. And we've got to set the polarity. So normally in our, go to the chalkboard, our GPIO pin, was low and high. GPIO, and it could be like ground and 3 volts. And this will be called high, and this will be called low. So if it's going along at low and then it goes high, we call this low to high, or alternatively rising edge. If we're high and we go low, we call that high to low, or falling edge. So we can set up different behaviors for our GPIO TE module based on which thing happens. So it can either be don't do anything, I think that's 0. It can be react to low to high. I wonder what that number is. Low to high, that's 1. High to low, that's 2. And then any change, 3. So this is recorded in a 2-bit format. 0, 0 is nothing. 0, 1, that's only low to high. 1, 0 is only high to low. And 1, 1 is both. So in our case, we actually want low to high. When you click that button, as you click it down, it goes high. Or as you release it, it goes high. I'm not sure. I think as you click it, it goes high. Sometimes you want it that when you release a button, it triggers. And then I think that's it. Initial value, no, that's fine. That's all we need to do here. So we need to say, look at this channel, find one channel of GPIO-TE, say, be looking at pin 0, port 0, pin 14, make sure you're in event mode, and your polarity is going to be low to high. So let's do it. Luckily, I've already got my GPIO events in 0 config register ready. Well, there it is. That's the config register for GPIO-TE. And I want to load that into R0. I'm really living dangerously, not using any sample code. I've got it on my other screen, and we'll see how long it takes me not to refer to it, because I really don't want to mess this up. And it's in your lab there, so you're not going to have to write this from scratch. We provide it for you. So I'm going to set up a configuration for that number. And in fact, what I want to do is combine a couple of little assembly directives to do the configuration that I want. Oops. So I need to set mode equals 1. I need to set, oops, this one. I need to set pin p cell equals 14. I need to set port equals 0. I need to set polarity equals 1, which is low to high. And I know that this first one is going to be bit 0. That next one there, P cell, is B. That's bit 8. Port is C, which is bit 13. And polarity is D, which is bit 16. I am going to refer to my code because I feel like if I make a mistake, it's going to be embarrassing. So, excuse me for a minute. Make sure I've got the right thing here. Oh yeah, I know what I'm doing. So, how do I do this? I'm going to just use this assembly directive, all the stuff in the parentheses, to kind of make a binary number. So it's a binary number that's going to have a 1 at bit 0. It's going to have a 14, which is going to take up 4 bits, starting at bit 8. And it's going to have a 0 at bit 13. Well, that's sort of obvious. I could skip that if I wanted, because it will default to be 0. And it's going to have a 1 at bit 16. I could do this with like 6 lines of assembly, but I can do it all in one line this way. If I just put a 1 in there, that will be the same as making as doing this, OX1 or OB1 or just 1. But I want to combine a few things. So I'm going to have a 1. That's a 1 at bit 0. I'm going to have a 14 at bit 8. So I'll say 14 left shift 8 times. And another OR sign. I'm going to have a 0 at bit 13. I could skip this, but it's nice to have it there just so I remember what I'm doing. And the polarity is going to be a 1 at bit 16. Which I think is correct, yeah. So now you can see, because I've got these OR symbols here, all of these little constructions are going to get combined to make a number for this register with the correct configuration. So this all happens in the assembler. The assembler does these calculations and makes the number that I need. I don't quite know what it is. I guess I could run my program and find out. The number that I need is OX10E01. And you can see I've got in there, in the binary version, I can't point to it, but because I'll move my mouse, but you can see I've got a 1 at bit 0. I've got what looks like a 14 at, that's 1110 at bit 8. I've got a 0 at bit 13 somewhere. It's just a 0. And then a 1 at bit 16. So that's the correct configuration number. And then what I'm going to do is store that 1 to R0. Store R1, R0. So far, so good. What do I need to do? So if this was setting up GPIO-TE. You can see this is going to take me the rest of the 2-hour lecture to get this done. 1. Set up GPIO-TE config for module channel 0. Step 2, what do I have to do? Oh, tell GPIO-TE to accept interrupts on channel 0. Where is that? In the manual. Interrupt enable set. So I need to use this other register, OX304 offset from the GPIO-TE module, to tell it that I really would like to have interrupts enabled for my channel 0. So you can see it's got A, B, C, D, E, F, G, H. That's the 7 channels, each represented by 1 bit. And all I have to do is to write a 1 to the channel that I want interrupts to be enabled. How am I going to do that? I've got my GPIO-TE in10 set, interrupt enable set register. Oops. In10 set. Cool, that's ready. And then I'm going to do the same thing. Equals 1, and it doesn't have to be, I don't have to send it anywhere. I just send it 0 up so I remember. So this is enable interrupts on channel 0. And then I'll store it. All right, that was my second step. Enable GPIO-TE interrupts on channel 0. Any questions so far, or are you just like wrapped in how complicated this is? Yeah, remember this stuff inside the brackets is the assembler doing the work. Inside is the assembler doing some maths, not the CPU, not the microbit. I learned that trick from my tutors, would you believe? It's lovely to have tutors who are really clever and work out clever ways to do things, because I wouldn't have known. I don't know. They're the ones reading all these manuals and getting obsessed about them. I hope you do too. It's really amazing what I find students work out over the course of a course like COMP2300. Next thing to do, we need to enable the GPIO-TE interrupt within the NVIC. The NVIC was the nested vectored interrupt controller of the Cortex-M4. Enable GPIO-TE interrupt in the NVIC. Now, this one is a little bit trickier because I've got to go into the other manual. I've got to go into the ARM v7M architecture reference manual, and I need to go to somewhere. Where is that going to be? Part B something. Got it written down here. B.B3, yeah, system address map. To tell me what I need to do. Oh yeah, the system address map has all of the different addresses of different parts of your Cortex-M4. So there's some, remember the memory map, there's some addresses that are specific to the CPU, owned by the CPU, and there are some which are owned by the peripherals that connect to that CPU. So typically, you've got these things. This is the memory map. You've got your code going up to from OX000 to OX1FFFF, then your SRAM, OX200 to 3FFFF. That's a bigger area, really. Then you've got your peripherals. They either start with a 4 or a 5. Then you've got your regular RAM. Might be a different kind of RAM that has behaves more like the RAM on your big computer, which we don't really talk about in this course. Might have cache support, etc. Then some other RAM in the 8s, and then some devices, and then importantly at the end, we've got these things that start with an E, which are the system memory mapped registers. So all of the peripherals which are built into the CPU, like the SysTick timer, like the NVIC, are going to be controlled through the E's, E starting memory locations. So we're going to have to find out what these things are a bit later in here. The nested vectored interrupt controller, here we go. That's an integral part of the ARM v7M exception model. And it does various things. I'll let you folks read this complicated document here, but I'm just going to skip to the point where we look at the interrupt set enable register. Very important. So we're going to do the same kind of thing. We just said to the GPIO-T, please listen to interrupts on channel 0. And now we're going to say to the NVIC, please listen to interrupts on channel GPIO-TE. And this one, I don't know where it is. Oh, here it is. Whoop. There's various ones. Each one of these registers, ISA 0, ISA 1, handles 31 possible interrupts. There's a total of 495 possible interrupts within the Cortex-M4 architecture. Not all of them are used on any particular microcontroller, and in ours, not that many are used. Not nearly that many different interrupts, but there's just sort of the capacity there to have these ones in the memory map. And just to skip ahead, you can see the next interrupts are the NVIC interrupt priority registers. So that would be defining which interrupts go first in a 2-interrupt situation. So we need to talk to NVIC ISA 0, and I think we need to enable the bit corresponding to the the interrupt we're talking about. So on writes, enable interrupt. We need to write a 1 into that value. And I happen to know that we're talking about interrupt number 6, which is a bit weird for me to know that off the top of my head, but that's part of the microbit architecture, that is interrupt number 6. So we're talking about interrupt NVIC ISA 0. There's its memory address here. I had that one prepared earlier so I wouldn't forget. Well, letter R0. And I'm going to do exactly the same thing. Letter R1 equals 1 left shift by 6 times. Enable TE interrupt in NVIC, which is ID equals 6. Store R1 R0. Now folks, believe it or not, we are done, which is super cool. I'm just going to go into enable my NOP loop here, because I want my program to have something to do while waiting for an interrupt, so I need to have a NOP loop. By the way, how did I know that it was ID number 6? I think if we go to the start of the microcontroller manual, block diagram, I forgot what it was, something like initial setup. Someone will remind me of the page for that in a minute. Oh, instantiation, that's the one. This tells you what ID every single thing has. So the ID corresponds to the number in the interrupt vector table. Number 6. And also, you can also work it out because it's got that number within the address. So if an interrupt is coming from GPIO TE, it's going to come in on channel 6. Have I got my handler? Yeah, I got my handler. My handler is not doing anything except having a NOP. So let's run my code and see what happens. Hope it works. Did it work? Yeah, it worked. I set up my interrupt. Blah-de-blah. Set up the ISA, set up the INVIC. All right, and now my code's running. So how do I know if an interrupt occurs? I guess I could press the button, right? But like, oh, it's handily stopped. I think I already had a breakpoint set up there. If I set up a breakpoint at that NOP, I'll delete that breakpoint, set up a breakpoint at the NOP here, inside the interrupt handler. When I press play, my code is just going along, running like, hasn't got a care in the world. And if I click on the button, it stops at that breakpoint. So now I can do some stuff in reaction to having that button happen. And what happens if I press play now? I actually end up right back there. Why is that? I'll let you just posit a few theories about why that might be the case. That when I press play, I just end up right back in this GPIO TE handler. It exits it, it runs BXLR, and then goes into my NOP loop for exactly 1 cycle, and then ends up right back in the handler. What have I done wrong? It's probably a million messages. Sorry, I haven't been checking them. There's a few people feeling slightly lost in the chat. I've seen there's some from 10 minutes ago. Yes, feeling slightly lost. We'll go back over the slides in a minute. Does it go to... I'll go back on the questions in reverse order, but I'll tell you the answer here, unless anyone's got a thought as to why this is the case. The answer is I need to do a thing called clearing. So normally when an interrupt occurs, you've got to clear it in some way. And in this case, what I've got to do is clear the interrupt within the GPIO TE module. questions in reverse, in chronological order. Someone asked, does it mean that we can only listen to 8 interrupts by the GPIO-TE? In fact, the GPIO-TE can only have 1 interrupt. It can listen at any time on 8 pins and connect those 8 pins to that 1 interrupt. So there's only 1 interrupt for GPIO-TE. It's called the GPIO-TE interrupt in the NVEC, and it can listen on 8 separate pins. And if you want to listen on a different pin, you're going to have to stop listening to one of the first ones. Usually that's not so much of a problem. Someone's asking, what is channel 0 again? Ah, channel 0. Well, the way that, if I go back to my lecture, the GPIO-TE controller, which communicates interrupts to the NVEC, which is going to actually make the interrupt happen in your program, this has 8 different channels. 1, 2, 3, 4, 5, 6, 7, 8. Or to 7. And in fact, we're telling the GPIO-TE controller when we configure it to connect channel 0 to pin 14. So it's going to watch that pin on our behalf. You might notice that I actually didn't set the direction of the pin. I didn't set it to input. I didn't do any pin setup. Because it does it for you actually on your behalf. So there's 8 different channels that can listen to 8 different pins. So if we want to listen to button A and B, well, that's great. We can have channel 0 listen to button A, channel 1 listen to button B, channel 2 we might do something else with it, channel 3, etc. They might listen to different pins or do different things. Someone's feeling slightly lost. Good. I'm glad that you're feeling lost today, because you're going to have a big week of interrupts ahead of you. In fact, you're going to have a big 2 weeks of interrupts. Week 8 and week 9 is all interrupts all the time. By the end of week 9, you're going to be an interrupt expert. But I'm really pleased that you're here listening to this today being confused, because as it turns out, learning about a thing multiple times, if you start out being confused, eventually you learn it. Ooh, can we do an interrupt when button A and button B press down simultaneously? That's a really good point. So we'll think about how to do that in a minute, because I haven't really talked about the interaction between button A and button B. And in fact, I haven't even tried it, so I have no idea what will happen. I've only tried button A, and I just assumed I'd be able to work out button B later. So, oh yeah, we have one more thing to do. We have to clear the interrupt in the GPIO-TE module. Back to the microcontroller manual. Don't you love it when I've got a lecture with all these manuals open? That's when you know you're into the good stuff. Interrupt enable clear. So what we have to do, having received this interrupt, we're going to have to clear the interrupt marker within our interrupt enable clear register in the GPIO-TE module. So we do that inside. Let me do some stuff here. Do something in response to the button. And then we want to load up our GPIO-TE in 10 set. Oh no, events in 0. We clear it in that register, because every time that register is set, it triggers the interrupt. So we have to tell it to stop doing it. Yeah, events in 0, we can read this register. Letter R1, R0, we'll just read to find out if it really was a channel 0 interrupt. I mean, we might not know. And then we'll store a 0 into that. Don't need that NOP anymore. I'll still have it for my my breakpoint. Just hold on to that thought about the 2 interrupts at once idea, because it actually is not as hard as we think, I believe. Someone said they're confused. Why do we have to clear the interrupt? So I'll tell you why in a minute. So we go down here in my program. I'll just press play. I should be I'm in the NOP loop at the moment. Press play again. Click my interrupt. And now I'll run this code I've got here. I'm going to load up the value of this register here, GPIOTE events in 0. Load up that code. It's a 1, so I know that really was because I clicked the button that triggered triggered events channel 0. Then I'm going to clear it out and go back into my program. And now if I run it, I'm still in the NOP loop. So I actually am now able to escape my interrupt and not just keep on ending back in that interrupt. So I'm pressing play, press stop, press play. Or maybe not. Does it keep doing it over and over again? I think I was pressing the button accidentally. Every time I click, I end up back in the click loop. So why do we clear the interrupt? I believe at this stage, I'm going to say I believe, I'm still learning about GPIOTE. Let me put it that way. I finally read this section of the manual the other day. I'm just going to go to where it actually explains it. Pin events and tasks. Oh well, maybe I can't remember where it was that it actually tells you why that interrupt keeps happening. Oh, no, that's not right. Well, intent clear, intent set, events in. My understanding was that whenever the GPIOTE module detects that change that you've set up within the pin, it writes the bit in the events in register. And if that bit is set in that register, the GPIOTE module is just going to keep triggering interrupts. And the reason is that the GPIOTE only has one interrupt line into the NVIC. So if you had 8 pins, 1, 2, 3, 4, 5, 6, 7, 8, connected to each channel, 8 pins connected to the 8 channels of your GPIOTE module, and they all get triggered, all of those 8 registers, the input registers, are going to have their bits set, and that means that you might need to have 8 separate handling routines to run them. But you've only got one event handler. So if I set up the event handler for channel 1, it's also going to be GPIOTE IRQ, because the NVIC only has one entry for this whole peripheral. So this is a handy way of letting us use one entry in the NVIC to handle multiple pins at the same time. But if we had multiple pins being handled simultaneously, we'd have to do some logic to check which pin or multiple have been triggered. So I did that here with channel 0, but I could then do it for channel 1. Same thing. In 1. I haven't actually set up this register. So then I might want to clear 1 and then let another interrupt happen immediately, clear the next one, another interrupt happens immediately, clear the next one. Or, as someone asked in the chat, I could check, put these into different registers, put that into R3, and then check if R1 and R3 are both set, both 1. That would mean that both buttons have been pressed. So I can handle the both buttons pressed case within one single interrupt handler, which is pretty handy too. So that's cool. Not as complicated as we thought. Someone, I'm sure, has a question out there for me. Who has a question for me? This is complicated. It's complicated for me. You can see how hard I had to think to get it to work. I'll put that GPIO TE events 1 register in there as well. Let's get both of these things running. It's address OX100 plus 1. Why was it so much harder on the disco board? Yeah, good question. I'll tell you that in a minute. One. 40006104. It's the next register in memory. 4 bytes forward, 1 word forward. Okay, let's set it up for both. Our config is 1 as well. Sorry, whoops. We don't need anything else. We'll do config 1. What was the other port? Port 23. Everything else is the same. Now when we enable interrupts on channel 0, we need to interrupts on channel 0 and channel 1. And channel 1. 4, 1, 1. Okay, so we've got 2 interrupts. We don't have to do anything else about the NVIC, that's all the same. And I'm not going to do the event handling, I'm just going to check which button I pressed. So I'll run my code here. Hopefully that all works. Who knows if this is going to work or not. I've literally never tried this. This is what live coding is. So I'm going to check. I'll press button B this time. It did it! It worked! First time. That's pretty good. GPIO TE events in 0. Let's check that. Having a look. It was definitely not a button A press, but it was a button B press. Wow. R3 is 1 for button B, which is cool. Folks, I think it would be very hard to recognize a click of both ones at the same time, because you'd have to close both contacts simultaneously, or very, very close in time, much quicker than you would probably be able to do as a human. So if you clicked them together, even if you think you clicked them together, it's going to have one interrupt and then another interrupt. So that's going to be tricky this will be tricky physically, or it will be harder to accomplish this physically with your fingers and your body than it will be to do it as in programming. Really the only way to do it will be to have one switch that's hardware wire connected to both inputs. Hard to do physically. Question was, why was the disco board so much harder to deal with? The disco board had this annoying thing where whenever you wanted to use a peripheral, you had to turn it on. So peripherals weren't turned on by default. So you had to do a lot of turning on of things in something called the something and clock control register. The RCC register would enable clocks for different things. You had to do it for GPIO all the time. Everything had to happen in a much more annoying way. Then it had a much more complicated GPIO thing that was like the GPIO TE called the external interrupt controller. It sucked. I hated that thing. The GPIO TE is much more interesting. It's simpler. It has less channels. The GPIO XT thing had like 16 channels, I think. So it was definitely the disco board had a more capable chip in it. But I mean, physically it was bigger. Where's the disco board? Here's one. That's a disco board in a little 3D printed case I made. Like, check this out. This is the size of the disco board chip. It's like as big as my finger, and the one in the microbit is like a quarter of the size. So it's really a completely different kind of proposition. This chip is much more powerful, has many more pins. It's more powerful in some ways. It's got more peripherals, it's got more stuff on it, but it's actually slower than the microbit chip. And it doesn't have Bluetooth. The microbit chip has Bluetooth, which is cool. Anyway, long story short, it's a weekend lecture, so I'm just going as long as possible to make things very complicated for everyone. Any other questions? Someone else has surely got to have a question for me, because we've only got a few minutes left, really. Folks, we did it. We made buttons work unbelievably, right? How could we possibly get that done in one lecture? I think it's pretty good. I think you've been a great audience today listening to this stuff. If you want, you can have a look in the code in the lecture today. You'll also be seeing it in Lab 8. We do have multi-button presses on keyboards, right? Yep, we do. Control Z. But they work differently. I won't go into that. Let's just leave keyboards out of it for the time being. You can go and watch Ben Eder's video on how does a USB keyboard work if you want to know more. It involves an oscilloscope. Can we also have the 3-volt and ground pads trigger interrupts? No, they're not GPIO pins. The 3-volt and ground pads, that one is literally just like connecting a wire to a battery. So it's always 3 volts. It's not an input pin. It's not even connected to the microbit. Neither is the ground. Well, they are connected, but they're used to power the microbit. So they're nothing to do with the way that the CPU works. Can I update the lecture slides? Oh, sorry. You mean the PDFs? I'll update those tonight or directly after this lecture. I just have to run a script. Someone said an aside about the assignment, isn't a 5x5 board a bit low res to display a recognizable image of a pet? I didn't ask for a recognizable image. I asked for something you have to look after, something that's engaging, something that's fun, something that uses interrupts. I'm not asking you to draw a puppy. I mean, some people had amazingly compelling emotional stories involving 2 pixels in the assignment, in assignment 1. I was blown away by what people can do in assignment 1. Some really cool things. Someone had a sphere rolling around. Wow, that was cool. I don't know how you did that. That was whoever did that. It was a wild experience for me. One more thing before we stop. Let's work out what's going on with these registers, hey? Whoops, not VirtualBox. Just for fun, I'm gonna litter up some weird stuff into my registers. A, B, C, D, E, F, G. No, A, B, C, D, E, F, O. 1, 2, 3, 4, how about that? Letter R0. 8, bad food. Hope this is not giving anyone bad flashbacks from the exam. R2. OX. dead beef, letter R3, OX, FFFF, AAAA. Cool, so we just wanted to set up our call save registers so that they would be ready in case an interrupt happens. So there they are, all my call save registers. I'm running my code and then kablamo, an interrupt occurs. And my interrupt handler could be writing over those numbers. But let's have a look and see where they are. I promised you they were on the stack, didn't I? So we're going to find out where we're up to on the stack. Let's find out where we're up to on the stack. So we're up to, going to the memory viewer, I'm going to say look for OX2001 and like EF00, start with that, and then it'll go, view memory. That's the one, OX2001 EF00. I'm just looking at the value of stack pointer right now, and I want to see this many bytes. Where are my things? Stack pointer. Oh, the stack pointer goes backwards, doesn't it? Now I'm messing myself up. It doesn't count up, it counts down. I needed to start there. It's too late on a Monday evening for me to remember how to do things. Memory address OX2001 EFE0. I'm being a huge brain right now. Just give me 128 bytes of memory. And its last used location was E. There's my numbers. FFFFAAA. Dead beef. Ate bad food handily in little endian order. A, B, C, D, 1, 2, 3, 4. So they're all safe and sound on the stack. Isn't that cool? So they've been put there. The last one that was put there was 1, 2, 3, 4, A, B, C, D. Then ate bad food, then dead beef, then FFFFAAA, and then a bunch of other stuff related to the flags and the PC and everything that needs to be stored. So now you know that when you run an interrupt, your call save registers are going to be safe and sound. Ooh, can we enter an interrupt when we release the button but not push it? Absolutely you can. I think that would be if you use the mode. The mode was, not the mode. The polarity 1 is low to high. I think if you use polarity 2, oh, no, it's way further back. No, way further forward. If we use polarity 2, that will be high to low, and that would be when you release the button. That would run an interrupt. Final couple of questions. With regards to working with Bluetooth, is there any capacity to work with 2 microbits? Or we would have to sort that out ourselves. Well, I don't have enough microbits to get over on 2. We will actually, it's something you could sort out yourself. You're perfectly happy to buy 2 microbits and run it, but you can only submit 1 program. So you'd have to have a program that connects to itself in some way. So if you want to do an assignment that involves Bluetooth and connects to other microbits and you can manage to make it work, be my guest. Go as far as you like, run a mile, fly to the moon. Tell us about it in the design. Tell us about it in the design document, and if we really need to have two microbits, we, the tutors, can figure out how to mark it. But the assumption is that it's a one. The assignment here is a 1 microbit assignment. You will do a little bit of network work over a wire in the labs later in this course, but after this chunk of GPIO labs. I mean interrupt labs, not GPIOs. Any more questions? I don't think so. Wow, okay. What a lecture, eh? I really wanted to get this topic done when there would be people watching, so I'm so thankful that you were here to watch. I've got plenty of readings about interrupts for you to do if you want to. I just want to point out, I've put a couple of extra references on the website, some books, in fact. These books are actually useful, particularly in this part of the course. You'll want to have a look at this book called Essentials of Computer Organization and Architecture, which is kind of this fly-through of things like operating systems, networks, memory, CPU design, different architectures, interrupts. All of these things which are like the high-level concepts are introduced in a really great way in this book. It doesn't talk about Cortex-M4, it talks about a CPU, but it's like a fake one. So that kind of that irritates me. I like to talk about real things, not fake things. So, but it's still useful for learning about interrupts. And then next week, we're going to talk about where we were and what we could be doing in our code to change what's been put on the stack after an interrupt happens. And in particular, we're going to be investigating what happens if you change PC. So if you change PC on the stack after an interrupt happens, that means that when your program returns for the interrupt, it's going to be in a different place than when it started. So I'll let you think about the implications of that one. We will join together again on Thursday this week. Have a great time in your labs this week. You're going to have an excellent, fun time playing with interrupts. Now that I've thoroughly confused you today, you can spend the entire lab having your tutors unconfuse you. So, I will say goodbye, and we will join up again on Thursday morning. Have a great week, folks. See you then.